Okay, good morning, good afternoon, good evening, and good night, laboratory assistant and also lecturers. My name is Palito, and my NPM is 240-644-8272. And I'm going to present about metallography and heat surface treatment. Okay, so for the metallography, I've got question B. It is about a medium carbon steel is subjected to a quenching process using different cooling media, water, oil, and air. After austenitization, analyze how these different cooling media affect A. Cooling rate, B. Phase distribution, martensite, bainite, and perlite, and C. Hardness distribution from the surface to the core. So I'm going to explain my answer. My answer is the choice of quenching medium plays a critical role in determining the thermal history of the steel, which directly influences phase transformation, behavior, and the resulting mechanical properties. So for the A, it's a cooling rate. So water defined to fastest cooling, high severity, oil divides to medium cooling rate, air divides into slowest cooling, and the order is water, oil, and air. So the cooling rate depends on how fast the medium removes heat. Water cools the fastest, oil is the moderate, and air is the slowest. So the order is water, oil, and air, which controls the phase transformations in the steel. So for the B1 is the phase distribution. It is about the water quenching mostly martensite, very little or no bainite or perlite, coil quenching mixture of martensite and bainite, small amount of perlite possible, air cooling mostly perlite and ferrite, also almost no martensite. So the explanation is about the phase distribution that is controlled by the cooling rate during quenching. Fast cooling water suppresses diffusion and forms mostly martensite. Medium cooling oil allows partial diffusion, producing a mix of martensite and bainite. Slow cooling or air gives enough time for diffusion, resulting in perlite and ferrite as the dominant phases. So for the C1 is the hardness distribution surface to core. So the first one is the water surface that is very high hardness or martensite. Second one is the core slightly lower that may contain bainite or perlite. The third one is the large hardness gradient, and the fourth one is the oil surface that high hardness martensite, and also the core moderate hardness that bainite plus martensite, and there is the more uniform than water, also air surface and core, low hardness perlite or ferrite, and lastly is the very uniform. So it explains how hardness follows the cooling rate. The surface cools faster, so it is harder, while the core is softer. Because water gives the biggest difference, oil is more uniform and air is low and uniform. Okay, so for the next question is about the heat surface treatment or HST. I've got question 5, and it is about to explain the fundamental differences between TTT and CCT diagrams in terms of process conditions and also cooling trajectories. So my answer is, in the study of the phase transformations in steels, this understands how austenite decomposes is critical, while both diagrams map the transformation of austenite into various microstructures like perlite or bainite and martensite. They also reflect the different thermodynamic and kinetic realities. So the comparison is TTT versus CTT diagrams. So the first one is the process conditions. TTT is the isothermal. So this transformation occurs at a constant temperature after rapid quenching that is used for specialized process like alttempering. Now the second one is the CCT, that is the continuous. It transforms occurs during constant cooling from the austenitizing temperature. And also this represents standard industrial heat treatments, quenching, and also normalizing. So for the second one is the cooling trajectories. So the first one is the TTT path that is represented by a horizontal line or isothermal hold. And also the CCT path represented by a downward curve, the cooling rate DT or DTS. And lastly is the kinetic shift. In CTT, the transformation nose shift to the rider longer time and lower temperatures due to delay in the nucleation during continuous cooling. And the third one is the microstructural outcomes. The bainite formations readily produce a via TTT isothermal holds. So in CCT, the bainite region is often bypassed or suppressed by the perlite nose in the plane of carbon steels. And also the last one is the critical cooling rate. That is only the CCT diagrams that define the specific cooling slope that is required to bypass the nose and achieve 100% martensitic structure. So that is my answer for the HST. So this is my reference that I got, and thank you for listening and watching.